Good afternoon and welcome you all to this session of Conduction and Convection heat transfer. Last class we were discussing heat transfer through extended surfaces known as fins. The situation is that extended surfaces are attached to a base surface to enhance the rate of heat transfer from the base surface. And these extended surfaces provide additional surface area for convective heat transfer from its lateral surfaces, along with conduction through these surfaces. And through this, that is by providing additional area for convective heat transfer from lateral surfaces, these fins or extended surfaces enhance the rate of heat transfer from the base surface. And what we discussed, we formulated the differential equation for temperature distribution by applying the conservation of energy to an element in consideration of one-dimensional heat conduction through the fins, that is the extended surface, along with the convection from the lateral surface. And we have solved for the temperature distributions for different cases or situations of the field, which impose the different boundary conditions for the solution of the differential equation for temperature. Today, you just have a overall summary. Before that, I tell you different types of fins that are used. Overall view. This is the straight rectangular fin is the most simple case, that the cross-sectional area of the fin is constant, same. This is the base surface, as I have just told. This is the extended surface known as fin, which provides additional surface. This surface, top, bottom, this surface, these are the surfaces, this lateral surface, all these surfaces, additional surfaces for convective heat transfer along with the conduction through this fin along this direction, for which the heat transfer from this base surface where it is attached is enhanced. This was discussed, and from the conservation of energy principle we developed the differential equation for temperature, and we solved it under different boundary conditions, different situations. These are different types of fins, straight fins but non-uniform cross section. See, this is an annular fin. Sometimes it is known as circumferential fin. In a cylindrical chamber, these are used sometimes in heat exchangers. This type of fins are used, this circumferential fin or annular fin. Number of fins may be used. Here also there may be number of fins. Only one fin is shown. This is one fin with non-uniform circular cross section, like a conical shape. Okay, circular cross section. This is sometimes known as fin with non-uniform circular cross section. This is the same thing in a cylindrical tube, where the heat transfer from the surface, for all these cases the heat transfer from the base surface is enhanced by attaching these extended surfaces or fins. Here the fins are longitudinal, parallel to the axis of the cylinder. That's why this is known as longitudinal fins in cylindrical tube. This is a fin, similar type like this, is a parabolic profile, non-uniform. So different types of fins are used. This you can get in any classical textbook, nothing great. Now these are the things which we discussed last class, that we first discussed infinitely long fin, where the base is at a temperature Tb, base temperature is same for all cases. Now if the fin is infinitely long, we impose the boundary condition from our physical sense that ultimately the temperature at this exposed end becomes the surrounding fluid temperature T infinity. In that case, our temperature distribution is exponentially decreasing e to the power minus mx, T minus T infinity, Tb minus T. Tb is the base temperature, T is the temperature at any section x. So at x tends to infinity, it is T infinity. So curve goes to T infinity. Another thing is that this type of solution at the same time gives a zero slope. dt dx is 0 at x is equal to infinity, when x tends to infinity. And the heat transfer rate accordingly is given by this hp or phk root over tb, root over phk tb minus t. Case 2 we discussed fin with insulated tip, where we impose the boundary condition dt dx 0. That means fin tip is insulated, no heat is being transferred from this exposed surface, this surface. That means all the heat which is being extracted from the base is being convected from the lateral surfaces, so that here the heat transfer is 0. That is the physical concept. Boundary condition is imposed in terms of the temperature gradient. Whenever there is an insulated surface, adiabatic surface, heat transfer boundary condition is, in conduction dt dx is 0, because heat transfer is 0. Like your fluid mechanics, shear stress is 0, du dy is 0. One dimensional case. Similar thing, so that the temperature profile is that it does not attain the T infinity temperature. This temperature is higher than T infinity because of this insulation, but the slope is 0. The shape of the curve is such it becomes parallel to the abscissa, so that dt dx is 0. Number 3 case, that also we discussed in the class, that here we impose the most practical situation, that we don't insulate this, it is open to the atmosphere. That means the fin shares heat by convection through this lateral surface, this bottom surface, okay, the side surfaces, both the sides, and also at these exposed surfaces, at this end, extreme end. So these exposed surfaces, heat transfer, there we prescribe the condition of surrounding fluid T infinity. So therefore, while solving the equation within the fin at x is equal to L, here, well, this diagram is little wrong, I am sorry to tell you, probably it is wrong from the place where it is taken. This point, this line should coincide with the length of the fin, because this part is outside. So it is wrong from the place where it is taken. You see, even the published things, and sometimes this is because of our overlooking the error while reading the proof. So therefore, here what happens, the temperature changes and it has a slope, not zero slope, which determines the heat transfer minus k dt dx, and should be matched with the convective heat transfer at this interface, that is this solid exposed surface with the surrounding gas, so that this slope is matching with this. And this is the temperature distribution by convection after this. That means from this surface there is a decrease in temperature in a thin film due to convection, which will be dealt in details in convection classes, first class when we will take convection, heat transfer. So this comes to T infinity. This just to understand. And in this case, with this type of boundary condition, it becomes a routine calculation with little complications. Algebraic manipulations are little tedious, so that we get a temperature distribution theta by theta b. Nomenclature, you know, theta is the excess temperature over the surrounding fluid temperature. Theta b is the base temperature over the surrounding fluid temperature. That means theta are the temperatures over the excess fluid temperature. So accordingly, the heat flux is given by this expression. This gives hyperbolic function. Another case where we fix the fin temperature at the end. That means fin temperature is fixed at the end. By some arrangement of cooling fluid, we keep a fixed fin temperature. We are not much bothered how it is done, but we think mathematically as if the temperature is given at x is equal to LTL. So we solve the equation, we know the boundary condition at x is equal to L, T is equal to TL. In that case, the temperature distribution is like that, and it doesn't reach T infinity. And the temperature distribution, if you find out, it will be like this. Okay, so this is the fixed temperature at, fixed temperature at the end of the fin, temperature distribution and the heat flux. What is meant by fin efficiency? What is fin efficiency? Let us take this that this is the sorry. Let us have this base plate and we have this is not correct, the drawing is not. Let us not do this thing, let us think of we can do this, but this will let us think this way, that a straight this is the base and this is the rectangular fin, this is the fin. Now, fin efficiency. What is meant by fin efficiency? Fin efficiency eta F. The fin efficiency is defined like this. Now, if the base temperature is Tb, the heat is transferred, an amount of heat is transferred Q from this portion of the base where the fin is attached, and this portion of the base where fin is attached, a huge amount of heat transfer takes place. Because of what? Because of this heat transfer from these lateral surfaces. You can show this surface like this also. That means the top surfaces, this surface, bottom surface, this surface, again this surface, back side, all these surfaces, the front side, these surfaces and these exposed surfaces, everywhere the convection, Q convection, Q convection. From this surface also, the lateral surface, Q convection. Q, this we already did in the last class, Q convection. And from this surface also finally convection heat transfer is there. If it is not insulated, that means this side, top surface, bottom surface, that means all lateral surfaces, convection heat transfer is there. Due to this large surface area, the convective heat transfer is huge, so that finally this heat that is coming from this base where it is attached is enhanced. That is the basic principle of fin. But one thing, what we assume that it is a one-dimensional problem, usually the large fin, so that we consider this direction is the x. Okay, that means this is the x direction from this plane. So at any x, the temperature is T, which is same in this direction, width of the fin, thickness of the fin or height, whatever you can tell, that means same temperature, but it changes with x, and this T is always less than Tb. That we have already seen, that temperature is maximum at this point and then slowly decreases to a temperature, and free stream temperature is T infinity. Now with this knowledge in background, how does the fin enhances the heat transfer, the efficiency is defined as the actual heat transferred from the base, that means this portion of the base where the fin is added. Let us write this as QA, that is the heat transfer through the base. I am not writing it, I am telling heat transfer through the base with the attachment of the fin in actual case. So why I am telling actual case? This case is okay, this is actual. Why? That is because the denominator defines a quantity QB, which is the heat transfer, rate of heat transfer from the base where the fin is attached, if the entire fin would have been at the base temperature. That means the entire fin attains a uniform temperature, that of the base. When it can attain? If the thermal conductivity of the fin is infinitely high. So infinitely high thermal conductivity of the fin. Otherwise, in actual case, the fin temperature decreases along the direction x. But at any x, this is same for all the lateral surfaces. This we took in deriving the temperature distribution, the differential equations for temperature distribution from energy conservation principle. So this is the definition, that heat transfer, I may write this, rate of heat transfer from the base with fin. This is the actual rate of heat transfer, and this one is rate of heat transfer from the base if the entire fin is at base temperature. Now QB therefore can be written like this: if H is the heat transfer coefficient, with our nomenclature P as the perimeter of the fin, that means sum of this dimension, this plus this into 2, this side and the bottom surface, that is the perimeter, into the length of the fin. If this be the fin length, the length of the fin times the Tb minus, because the entire fin is at base temperature. So therefore the ideal heat transfer, that means considering the fin to be infinitely thermal conductive, so that having infinite thermal conductivity, HPL theta B. Therefore the expression of fin efficiency depends upon the expression of QA. If you take long fin where the fin length L tends to infinity, very large length, we know that QA is equal to what is QA? Root over HPKA theta B. So therefore, in this case, eta F is equal to root over HPKA theta B divided by HP L theta B, and this becomes, if you cancel it, 1 by ML, where M is given by our nomenclature, that root over, we denoted M as root over HP by KA. So it is very simple that you substitute the expression in the numerator for the actual heat transfer. In case fin with insulated tip, fin with insulated tip, fin with insulated tip, what will be eta F? Eta F will be, this is HPL theta B, and heat transfer which we derive, I have shown it also, it will be root over HPKA, same thing, but tan hyperbolic ML into theta B. M is the nomenclature root over HP by K, and this becomes tan hyperbolic ML divided by ML. So depending upon the cases, you can find out the efficiency expression. So therefore, the question of fin efficiency comes because of its conductivity. At the very first class I told that we are putting a conduction resistance, though we are adding a more convection area to enhance the heat transfer. But if the conduction resistance is very large because of very low thermal conductivity, so that there is a drastic drop in temperature along this direction, so heat transfer from the lateral surface may not be augmented that way, because the heat transfer depends not only on the surface area but also on the temperature difference. So therefore, there is a race between the two, that we have to be careful that the fin should not have a large temperature drop. It should have a high thermal conductivity, and the most ideal case is that thermal conductivity is such that the entire fin is at base temperature. So with this, if you compare, you define a parameter like this, which is known as fin efficiency. Now here we see a number of fins, array of fins, a system with array of fins. This is the base plate, number of fins are there. Here it is, there are 3 fins, it is shown. Base wall at a temperature of Tb and surrounding fluid T infinity. So here how do you define the fin efficiency? Same thing, but little calculation, that fin efficiency here it is defined as the Q from the system, fin array system. Q, can you see it? Q fin array system divided by Q from the same fin array system at Tb. That means the entire system is at Tb. What is the difference? Difference is that here fin array system, when we consider Q, then we have to consider the heat transfer from the fin, also the heat transfer from the unfinned portion. Okay. Now if we have a nomenclature like this, let us consider AF is the total surface area of the fin, total surface area of fin. And if we make this nomenclature, it is the total area total heat transfer area, total surface area, and this surface area means heat transfer area which takes part in heat transfer. Total surface area including both the surface, all surface area of fins plus uncovered portion. That means these are the uncovered portion. 80. 80 is the total surface area. That means uncovered portion plus fin. Then we can write here Q, the numerator QF, fin array system, Q fin system, Q fin system okay. Q fin system can be written as I can take this here because already I have told this. So Q fin system is the heat transfer from the fins. That means if AF is the total surface area of the fins, then H into AF into theta B. What is theta B? Theta B is, theta B, here I write, theta B is the TB minus T infinity. Now here what I want to tell you, that how we can write the efficiency of a fin array system in terms of the individual fin efficiency. If we assume the individual fin efficiency is eta F, which is constant same for all the fins, then we multiply this with eta F, gives the heat transfer from all the fins. HAF theta B considering fin at the base temperature. So this is the ideal heat transfer, and this is multiplied by the fin efficiency of the individual fin as it was defined earlier, gives the heat transfer from all the fins plus the unfin portion, that is A total minus AF, that is the area into H into theta B. H into theta B, and the denominator will be the total area AT into H into theta B. That means how to express this? If we know the total surface area of the fin and total surface area including the unfin portion plus fin, so minus the fin portion, this is the area of the unfin portion, AT minus A. This can be written in a simple expression taking AT, H, theta B separate term, 1 minus theta B cancels out, H cancels out, AT, H, theta B, H cancels out, 1 minus AF by AT into 1 minus eta F. Eta F, okay? Efficiency, eta F, QF, now sorry, it will be the efficiency of the array system, efficiency fin system, not QF. I am sorry, it is efficiency of the fin. I wanted to first start with this, with the numerator, okay. So I have done at the same time. So okay, I first started to write this expression in the numerator. However, doesn't matter. The numerator is the Q, that is heat transfer of the fin system, that is the heat transfer from the fins, that is the heat transfer from the unfin portion. So eta for the fin system is divided by AT H theta B, divided by the heat transfer of the entire base with the fins when they are all at the temperature TB. So when eta F then equals to 1, eta fin system also equals to 1. That means we can express the efficiency of a fin array system in terms of efficiency of individual fin. Okay. Now another important concept in practice I will tell you. which is very important for engineer. We define fin efficiency, okay, this is the definition, we understand. The ideal case is a highly conductive fin whose in superconductor, whose temperature is equal to the base temperature, and we define the fin efficiency, the actual heat transfer with the fins, and what is the heat transfer if the entire system with fins attains the same base temperature. Now question arises whether how much we gain by adding fin. Sometimes it happens that okay, there is a monotonic gain, but what is the return? Whether it is economic to use that after certain stage, under certain cases whether fins are really required or not. If we have a marginal gain in enhancing the heat transfer, then cost will not provide. You cannot judge from the economic point of view, because you have to purchase fins, you have to go for manufacturing, attaching the fin surfaces, the entire fin system has to be fabricated. So therefore a question comes, effectiveness of the fin, to judge whether it is effective to use fin. Effectiveness of fin, that means to judge this, let us define a parameter the similar way as the efficiency, but E effective, effectiveness. That means it is known as effectiveness, but frankly speaking, physically efficiency and effectiveness is same. Effectiveness of performance is efficiency, but here it is defined in a little different way. Efficiency is the effectiveness of its performance when it is performing. But now I will judge what is the difference between the two, that it performs or it doesn't perform. That means if we define effectiveness as Q with fin or Q without fin, efficiency by definition is always less than 1, because fin can never attain TB temperature. Like Carnot cycle, like 1 is the theoretical limit. But here also it is always greater than 1. With fin always heat transfer will increase. But how much? What is the gain? What is the gain? Let us see that. Now in a very simple expression, if I write that this is equal to efficiency for a single fin, for example, fin H, no, simple, yes, H will come, H fin area, surface area of the fin into theta b. That means simply I multiply with the efficiency of the fin, H heat transfer coefficient, A is the surface area that is provided by the fin. And what is this without fin? Without fin, base area theta b. That means I get an expression A by AB into eta F. This is so simple, but it tells many things. That means I gain by using fins because I have a huge value of A by AB. But I should also consider if eta F is also not very low. If you multiply with a high value with a very low value, if eta F is very low, my gain may not be very high. That means I am providing additional surface. But efficiency is not a function of surface area. You go through the expression. The answer to the question lies in the fact that with increasing value of H, with the increasing value of H, eta F decreases. We have to be careful about eta F. If you have a low eta F, there is no point. Gain is less, very first class. That's why I started fin by telling that it provides a conduction resistance. Though we create more surface area to enhance the heat transfer by convection, but it provides a conduction resistance. And this conduction resistance becomes more and the efficiency becomes less if you have a high heat transfer coefficient. So therefore, one has to judge this. But without going for any detailed analysis which is beyond the scope of this class, I tell you as an information that where H is high, usually fins are not provided because of low eta, and we cannot provide a very large surface area because not only the cost but the space is a requirement. Where I am installing this equipment with fins. So therefore, we have to be pragmatic enough to have a meaningful gain, which is the product of AF by AB into eta F. For fluid, especially liquid, which has a high thermal conductivity in forced convection, gives a very high heat transfer coefficient. In boiling, condensation, phase change processes have high heat transfer coefficient. There, eta is usually low. We do not usually give fins. Okay? And from a very ready common sense tells, when the heat transfer coefficient is very high, the exposed bare surface will be capable enough to transfer heat. Why you are adding, why you are giving him, you are a brilliant student, why you are giving him a tutor? He himself can make it up like that. So therefore, sometimes this question is asked, if you have a heat exchanger one side, liquid is going and turbulators are there to create more turbulence in the flow field, and another side, gas is moving with a low velocity, which side you will provide fin? If you tell sir in the gas side, you get full mark. But if you say sir in the liquid side, flowing with high turbulence, get out. 0. Because this is the concept, that effectiveness of the fin. That means fin should not be used where the heat transfer coefficient is high. This is because of this fact. Okay? Clear? Now after this, we will solve some problem. Let me have a very interesting problem that you can take this problem. In a specific application, a stack shown below, this is a stack, that is 300 millimeter wide and 100 millimeter deep. This is 300 millimeter wide, is a long one, cut, shown a particular section, and 100 millimeter deep. Contains 60 fins. These are the fins. 5 are shown, that means there are a number of fins. It is a very big size, 60 fins. Each of length L 12 millimeter. This is the length of the fin. This is 12 millimeter. And this is the thickness of the stack plate. This is 1 millimeter, 1 millimeter. That's why this is 14 millimeter. This is the length of it. 60 fins, each of length 12 millimeter. The entire stack is made of aluminium, which is everywhere 1.0 millimeter thick. That means this one is 1.0 millimeter. This one. This was not shown in dimension. This is written. The temperature limitations associated with electrical components joined to opposite plates, that means this plate, this side of the plate, dictate the maximum allowable plate temperature of 400 K. That means this plate should not be at a temperature above 400 K. The electronic components will be damaged. And TL is 350 K. This side, the plate, is kept at 350 K by an arrangement of air with a T infinity and H, heat transfer coefficient. We are not much bothered at this side because the problem is prescribed by fixing the 350 K this temperature. Determine the rate of heat loss from the plate at 400 K. That means, what is the rate of heat loss from the plate at 400 K? What are the value given? H is 150 watt per meter square K. T infinity is 300 K. These are the value given. H is 150 watt per meter square K, 300 K. Aluminium thermal conductivity, that means the material thermal conductivity, 230 watt per meter K. This is precisely the problem. So we have to find out the heat transfer from the plate. Now heat transfer from the plate is due to the heat transfer from the fins, which is the heat transfer from this area of the bases where the fins are attached, plus the heat transfer from the unfinned portion of the base, plus the heat transfer from the top surface of the plate. Okay, that you have to recognize to solve this problem. Problem is very simple. But one thing, this type of problem in examination, if it comes, we will give you the formula. Here we have to use this heat transfer from the fin, where the fin is fixed at two temperatures. That means this you consider as base temperature of 400 K. And if you consider the fin of a length L, which is given as, what is the length? 12 millimeter. The other end is what is the temperature? Other end 300 K. That means fixed temperature at the end. No question of mugging the formula, but the formula will be provided. Or even a big problem, you may be told that you derive this formula. That means you start with the governing differential equation. Theta is C1 e to the power mx plus C2 e to the power minus mx by control volume energy balance. Then theta b is C1 plus C2 at x is equal to 0. Then theta L is C1 e to the power ml plus e to the power minus ml. From there you can also derive. But if teacher is relatively better, he will not ask that routine derivation because it is tedious. He will tell use this formula for fins with temperature prescribed at two ends, base temperature and other end. So problem boils down to that. So now let me solve this problem. This is 100 millimeter let us have this tank. This is the tank. Now here this is the flow of air. Now this is the geometry, 100 millimeter depth, 300 millimeter width. This is continued. This is a cut section. Number of fins 60, fin length L. And this is a air flowing through this, which gives the convective heat transfer coefficient, which takes the heat from the lateral surface of the fin. This is the problem. Now let me first write the this thing. This is the plate. Plate temperature, let we write is at TB, base temperature, that plate. This is the temperature TL. TL is 300 K and TB is 400 K. 400 K and T infinity, that is the surrounding fluid, is at T infinity is what? T infinity 300K. TL is not 300K, 350K. Sorry, 350K, and this is 300K. Now let us write the equation, the expression for Q plate. Q plate is what? Q plate is first 2 fins. Number of fins, there are 60 fins. Identical fins. 60 identical fins. Hey, if fin efficiency could have been given, I could have been happiest man. Then we could have found out that its surface area times H times TB minus T infinity times the efficiency. But it is not given. That means either I have to mug up that formula or I have to derive. Mugging means what? Nowadays no teacher gives that. That you have to mug up and you just write that thing. However, if it is given, then it is good, but it is a tedious calculation. Let me see, don't mind. That formula is per fin root over HPK, all the nomenclature as the known to us as their conventional thermal conductivity, cross-sectional area, perimeter, heat transfer coefficient into theta B, Bapre Bap. Then it is cos hyperbolic ML minus theta L by theta B with all nomenclature known to us divided by sin hyperbolic ML. So this is the expression of heat transfer when theta B, theta L are fixed for a fin and number of fins 60. This is the heat transfer from the fin surface. Then plus heat transfer from the unfinned surface. What is the unfinned surface? That area is what? Unfinned surface is 0.1 into 0.3. Now I will put this value afterwards. Now unfinned surface we write this way. AF, A unfinned surface. Unfinned. A unfinned, that I will find out afterwards. Into H into, there is no problem, TB minus T infinity, right? Theta B. TB minus T infinity, right? Theta B. Simply, write simply theta B. If any problem, tell me. Then A plate is very simple problem, H theta B. This is only a tedious calculation, nothing else is there. Now you write down the values. H is what? H is 150 watt per meter square K. P is what? Perimeter. Tell me what is P? P is the perimeter. That means this way 100 plus, that means 0.1 plus 0.001 into 2. It is almost equal to 0.2 meter. Perimeter. Perimeter is what? This side. You understand the perimeter? That means this plus this. Okay. Perimeter is all right. Lateral surface. Depth is 100, then 1 millimeter. Clear? Okay. This is the P. Perimeter. Now what we require? K. K is what? What is K? 230 watt per meter. What is cross-sectional area? A of the fin is 0.001 into 0.1. is equal to 10 to the power minus 4 meter square. HPKA, everything is there. Now A unfin. A unfin. What is A unfin? A unfin equals to 0.3 into 0.1 minus 60 into 10 to the power minus 4. This is very simple. Meter square. Clear? That means this is the unfin portion, this portion. Plate area, A plate is 0.3 into 0.1 meter square. That means 0.03. Clear? This is the plate area, 300 millimeter into 100 millimeter. Unfin portion, this area minus the cross-sectional area of each fin times 60 times. That's all. Okay. So, fin problem, I am telling you, are all direct applications of the equations that we have developed. But you don't have to remember the equations. You will only derive the equations and use it. This problem is clear. Now, if you put all the values in the proper unit, then you will see that the order is like this. This value comes out to be, I tell you, 6631 watt. Unfin portion heat transfer is 375 watt. 375 watt. And the top surface of the plate 450 watt. This plate means top surface. A plate means this is top surface. This is top surface. This A means the top surface. A plate is the top surface. That means from here. Now one thing which I like to mention, a comment, that you see most of the heat transfer takes place through the fin. Is increased by an order of magnitude. This is because of what? A huge surface area provided by the 60 fins. Well, clear? Hello? Clearly understood? Yes. I cannot hear you. Can you come here and tell me? Bottom surface, this is the bottom surface, unfin portion. Only heat transfer from this plate. This is the bottom surface. This is the bottom surface. This plate. This is not required. The question is that what is the heat transfer from this top plate? This is not required. This the entire stack. This part of the stack is not. That is not required. Yes, correct. You are interested in the entire system heat transfer, but this is not. This is not asked for. It is only from the top plate. Okay, so top plate at the two surfaces. Bottom surface through fins and unfin. And you see through fins and unfin the ratio more than an order of magnitude. Okay? Okay? Which one? Which side? Which side? No side is insulated. These lateral surfaces, all these surfaces of the fin, they transfer heat to the air. That is the convective heat loss from the side that takes care by this formula, fin heat transfer. From the plate, top surface of the plate. This surface, this end surface of the plate, from the end surface of the plate, oh, that is neglected. End effects are neglected. He is telling that end surface of the plate. That means 100 millimeter into 1 millimeter, that cross-sectional area. Very good. That is neglected. A good question. That is neglected. That is not taken. Very good. If you take it, extra credit. Good. By neglecting that, that means these faces, he is good. That means from these exposed faces, this face and this face, which has a cross-sectional area of 100 millimeter into 1 millimeter, H times the TB minus T infinity. Good. No, that is neglected. Okay. Any other question? Now I will show you some other problems. Consider a stainless steel spoon partially immersed in boiling water at 100 degrees Celsius. Slowly. You may write it in your own language. Time is less, so all the words cannot be written, or you can in a kitchen at 30 degrees Celsius. Now immediately you compile in your own language. 100 degrees the base temperature and 30 degrees the kitchen temperature, means surrounding fluid. T infinity TB. The handle of the spoon has a cross section of 2 millimeter into 12 millimeter. Ho gaya. 2 into 12, 24 millimeter square is A. And extends 180 millimeter in the air, that is length of the fin, from the free surface of water. The spoon is extending 180 millimeter in the air from the free surface of water. That means the length of the fin. If the heat transfer coefficient at the exposed surfaces of the spoon handle is 20 watt per meter square K, that means in our language H. So immediately compile. H is 20 watt per meter square K. Determine the temperature difference across the exposed surface of the spoon handle. That means TB minus TL. State any assumptions required. So can you tell me, this is a fin problem, immediately you compile TB, T infinity, cross-sectional area, length. So what is the boundary condition? Which formula I will use or which formula I will derive? Theta is C1 e to the power mx plus e to the power minus mx. I have one boundary condition known, that 100 degrees Celsius is the TB. What is that boundary condition? What does it say? H case 3. Very good. Speak loudly. Case 3. That means it is a practical case. No insulation is there. Oh God. No insulation is there. This is not very infinitely long. End temperature is not given. That means there is a convective heat loss at the end. So that end, that is tip, fin tip, has a convective heat loss. So case 3. You will derive the equation. We have to derive the equation and use it and get it done. That's all. Another problem. So I am not solving these problems because these are only applications of our results. Now another problem. Okay. One end of a, this is one very popular type of problem. Most of the books have this problem. One end of a 0.3 meter long steel rod, 20 watt per meter K. This is usually the thermal conductivity of steel, is connected to a wall at 240 degrees Celsius, while the other end is connected to a wall that is maintained at 90 degrees Celsius. Air is blown across the rod so that a heat transfer coefficient of 17 watt per meter square K is maintained over the entire surface. If the diameter of the rod is 60 millimeter and the temperature of the air is 40 degrees Celsius, what is the net rate of heat loss to the air? That means fin with fixed end temperature. Okay, these are the representative fin problems. All right? Okay? So before concluding the session, a generalized formula summing up my lecture about one-dimensional steady heat conduction with generation of heat, thermal energy, without generation of thermal energy, cylindrical spherical or plane wall, and also fins with lateral convection can be summed up like that. If you consider a variable area wall and take this as the direction of heat flow x, which may be x, which may be r, whatever may be. I am denoting it as x, where the heat flux is there, which may not be same at all sections. If heat generation is there, we cannot say so. If the lateral convection is there, we cannot say so. That we have seen. Now let us consider a case that there is lateral convection. I take an element at a distance x with a thickness delta x, and I denote qx as the heat coming into this phase with the, in accordance with this nomenclature x, and qx plus delta x is the heat going out, and this wall generates heat which is specified by heat generation per unit volume Qg at a point, which is a function of x in general, or may be constant, whatever may be. Qg may be a function of x, may be constant, may be a function of t also, and implicitly function of x, because t is a function of x. That means Qg may vary with x and t. And also there is the convective heat transfer, as I have shown you, Q convection from the lateral surface. Now if I have to write the energy balance, then I can write that Qx plus del x, which is coming out from this section, is equal to Qx plus Qg into the area Ax. Ax is the area here, which is a function of x. That's why I am writing a x into delta x, and at the same time it continuously convects heat, just like leaking pipe. It is very similar to fluid flow through a pipe where the surfaces are perforated. As the fluid is flowing, the water is leaking, and ultimately the entire water is drained out. At the end, no fluid is coming, no liquid is coming. This type of problem is interesting, that from lateral surface the liquid is drained out. Similarly, the heat is being also convected out. Minus, now this convective heat transfer, to take care of, H is specified, T infinity is specified, and I use a nomenclature perimeter P, so that P delta x is my area, and at that location if the temperature is T at x, then this will be T minus T infinity. That means Qx plus del x is Qx coming, plus this is generation of energy minus the convection. Clear? Now Qx plus del x minus, I take it in this side, or I take this side, that Qx minus Qx plus del x plus Qg Ax del x minus Hp T minus T infinity del x is 0. Now Qx minus Qx plus delta x we have done several times, expanding this in Taylor series and neglecting the higher order terms, and then substituting the Fourier heat conduction equation. Qx is minus kx dt dx, kx ax dt dx. Qx plus del x is Qx plus ddx of Qx del x. That means it will be minus ddx of Qx del x, and that will be minus minus plus. That means ddx of kax dt dx del x plus qgax del x minus hp t minus t infinity del x is 0. Clear? Or we can write again this thing that ddx of kax dt dx plus qgax minus hp t minus t infinity is 0. And this is precisely the expression for one-dimensional heat conduction with generation of thermal energy and lateral convection. Heat is going out laterally. Now here, in a plane geometry, now in cylindrical coordinate x is AR, x is R, cylindrical rod, cylindrical wall. X is twice pi RL, flowing in the R direction. In a spherical coordinate, x is R and AR will be 4 pi R square. Clear? Now, if we consider that there is no thermal energy generation, this is the fin problem. Usually fins, no thermal energy is generated. If you don't allow the leaking of heat laterally, I told you a simulation, liquid is flowing through a pipe, if perforation is there at the surface, all liquids will be drained. That means there is no lateral convection, which we discussed earlier, then this plus this is equal to 0. And if you take no heat generation, this part will be 0. If we take thermal conductivity constant, this will come out. And if we take AX is constant, that is happening only in plane area, plane surface with the same cross-sectional area, then the most simple case is ddx of dt dx 0. That means we have a linear temperature profile. Okay, so this expression gives you, or if you write this in terms of qx, ddx of qx, then you get the expression for, that means another version of this is qx plus qgax variable area. That means this is the most general expression. These two are the same equation in terms of total heat transfer rate, in terms of the temperature. You can get a generalized expression for heat transfer rate and temperature distribution in any steady one-dimensional flow with or without thermal energy generation, with or without convection from the lateral surface. So fin is one application of the one-dimensional steady-state heat conduction problem, that extended surface, where one-dimensional heat conduction is associated with lateral convection, and this is taken care of in the simple energy balance. All these things, oh, very good, minus QA, nice, nice, very good. Well, any question? So with this derivation, this is the summary of all my lectures in steady state one-dimensional heat conduction. Application is the extended surfaces fins. Any question asked. The end of the entire conduction chapter, we will have one session for tutorial. Though I have solved number of problems in the class while taking this theory, few more problems will be solved. Teaching assistants will be there. They will solve problems, we will be there also. Any question? Before conclusion, I tell you that next class we will discuss two-dimensional steady-state heat conduction. and that will be taken by Professor Suman Chakraborty.